This is lecture 9 of Kardinalna aritmetika, cardinal arithmetic. Last week we met the axiom of choice and we saw various equivalent statements to and variations on the axiom of choice. And as I mentioned last week, the axiom of choice is perhaps the most famous axiom from set theory that impinges upon ordinary mathematics, in that there are many areas of mathematics, or practically all areas of mathematics, have theorems in them that rely on the axiom of choice for the theorems to hold. Or at least they're proved using one of the versions of the axiom of choice. For example, Zorn's lemma is often used. So today's lecture is going to be about such mathematical consequences of choice. It's going to have a slightly different structure from previous lectures. So what I'm going to begin with is I'm going to list a few mathematical consequences of choice and not go into any details. Then the main part of the lecture is going to be exploring two mathematical consequences of choice in a lot of detail. One of them is called Vitali's theorem. It's something to do with measure theory. We shall see what when we get to it. And the other one is a very famous, one might say notorious result, called the Banach-Tarski theorem, which again I will say more about when we come to it. The first half of the lecture is going to contain Vitali's theorem and its proof, and that part of the lecture is going to be examinable, and this will be a relatively short part of the lecture, the relatively short half of the lecture. The second part of the lecture is going to be about the Banach-Tarski theorem, and I'm going to give a fairly detailed outline proof of that. That part is really quite advanced material that is beyond the scope of the course, so it is not examinable, and so the second part of the lecture is optional. So I'm including it purely for your own interest if you're interested in such things. Right. Okay, so let's start. So as I said, I'm going to begin by listing some known mathematical consequences of the axiom of choice in different fields of mathematics. So this is a selected list, and that there are many other important consequences of choice in mathematics that I'm not including. So let's say what we're doing. So important mathematical consequences of choice. Include. So in the title, remember AC is our acronym for the axiom of choice. It's a very standard acronym in mathematics. So in linear algebra, there's a theorem that every vector space has a basis. So that's in linear algebra. If you've done some linear algebra, you will know that one works with vector spaces, and constructions on vector spaces, well, it's normally nice if you can give constructions in such a way that they do not depend upon a basis, because constructions on vector spaces should just depend really on the underlying vector spaces. Nonetheless, in order to give concrete descriptions of such constructions, it is often convenient to work with a basis, and also to perform calculations with constructions on vector spaces, it is often convenient to work with a basis. So it is useful, if you've got a vector space, to be able to assume that it has a basis in order to be able to work with that basis. And the axiom of choice gives us the nice theorem that says we can always make that assumption. Okay, so that's one consequence of choice. That's in linear algebra. Let's go to a completely different field, topology. So in topology, there's a very important result called Tikhonov's theorem, which is normally, of course, it's not an English name, but it's normally written in English like this, Tikhonov's theorem. And this says that the Cartesian product of a family of spaces that are compact, compactness is a very important topological property that is a sort of generalization of the notion of finite to continuous space, an appropriate generalization. It's kind of finite in extent in some ways. So I didn't finish stating the theorem. So the Cartesian product of a family of compact topological spaces is again compact. So the product itself is compact. So let's write that down. The Cartesian product of a family of compact spaces compact topological spaces is itself compact. If you don't know topology, it doesn't really matter. All you need to get from this is that there is an important theorem in topology that depends on the axiom of choice. In fact, there are many important theorems in topology that depend on the axiom of choice. I'm just choosing one of them here. So this is in topology. And in the field known as functional analysis. So analysis in mathematical analysis, as in mathematical analysis, but rather than of functions acting on, say, numbers, it's functions acting on spaces, vector spaces. So taking arguments, vectors, and so such functions are called functionals, and the field of study there is called functional analysis. And there's a very famous theorem called the Hahn-Banach theorem, one of really the central theorem, perhaps, of the whole area, of the whole field. And this theorem relies on choice. I'm not going, the statement of this theorem is rather technical. Basically, it says that if you have a functional defined, a linear functional defined on a vector subspace of the space you're working with, you can extend it in a well-behaved way to a linear functional on the whole space. All you need to know is that there is such a theorem. As I say, it's really a central theorem in the field of functional analysis. So here we're coming from a completely different area, so functional analysis. And let's say one other result I want to mention is something called another theorem an important theorem in mathematics that depends upon the axiom of choice is a theorem known as the Boolean prime ideal theorem. So I also want to mention that. Now, this is not a theorem of one of the main areas of mathematics. If you want to give it an area, this is really a theorem in Boolean algebra. That's not really one of the main fields of mathematics. But I wanted to mention this theorem because it's actually an important theorem that has applications. This theorem itself has applications in many diverse areas of mathematics. For example, it's used in the construction of ultrafilters, and it's equivalent to the completeness theorem in mathematical logic, and various Gödel's completeness theorem in its full generality in mathematical logic, and it has various connections like that. So this is another important theorem of mathematics that relies on the axiom of choice. And as I said at the start, this is just let's go to black. this is just a selection of results in mathematics that rely on choice. So to emphasize it's a selection, let's add an etc. So to suggest, which is true, that we could have extended the list kind of arbitrarily. And now I want to make a comment about these, a general comment about these kinds of applications of the axiom of choice. Let's take the theorem that every vector space has a basis as an example. So suppose we did not have the axiom of choice, and then this would not be a theorem. It would not be the case that every vector space has a basis. Would linear algebra suffer as a result? In some sense, it wouldn't really, because for important constructions on vector spaces, one can give definitions of the constructions that do not rely on a basis. And moreover, then for calculations and explicit descriptions of constructions that do use a basis, one could simply add to the theorems themselves that make use of these constructions or calculations, one could simply add the condition that to make it clear that this proof or theorem or calculation or whatever is only valid for a vector space that has a basis. So the quantification for all vector spaces could sometimes be replaced for all vector spaces that have bases. So pretty much I believe that one could do without such a theorem if one wanted to. But obviously it would be rather painful to have to suffer that in each time you used a basis you need to explicitly say for a vector space that has a basis, and to just have to be careful about distinguishing between vector spaces that have bases and vector spaces that don't have bases. It's kind of much easier, it makes life much easier if you don't need to do that. And so this theorem, every vector space has a basis, it sort of plays a role of tidying up the field of linear algebra. It would look a lot less tidy if this were not the case. The other results maybe are a little bit more significant in their content, but once again one could get around them if one did not have the axiom of choice by making suitable assumptions in the statement of theorems. And once again, that would just serve to make life more complicated, and so it makes life much easier and, in a sense, more beautiful to have the axiom of choice and to have these nice general theorems that tell us that compactness is preserved by product, that linear functionals on linear subspaces can be extended to functionals on the entire space, and so on. So the point I want to make is that the axiom of choice is playing a rather positive role in this case. So in the above cases, the axiom of choice serves to make the mathematics simpler and tidier, I would say. I'll just write simpler than it would otherwise be without choice. So what I want to do today is look at two other consequences of choice which kind of go in the opposite direction. Rather than making mathematics simpler and tidier, they make mathematics more complicated and perhaps less intuitive. They almost have a sort of discomforting nature. They're rather counterintuitive results. So let's So today what we're going to do is we look at two consequences of choice in which, I'm going to say consequences of choice again. So let's say two mathematical results in which AC has, I want to use the word discomforting. It does not comfort you. Makes you feel a little bit uneasy. So the consequences of the axiom of choice make one feel a little bit uneasy. Consequences. And these two results are called Vitali's theorem. So these are Vitali's theorem and this is from the area of measure theory. And if you don't know any measure theory, it doesn't matter, because what I'm going to explain is, it's going to be from first principles, and I think it's all quite intuitive at the level that we're going to do it today. So it's not going to require any background in measure theory to understand it. So this is the one we're going to do in the first half of the lecture. And then we're going to look at a very famous result called the Banach-Tarski theorem. And this is also related to measure theory, but explicitly it's also kind of a little bit related to geometry. I'm going to state it in a more geometrical form, which is its natural form, but it's a sort of strange geometry. A geometer would not particularly recognize it as geometry because of the use of the way in which the axiom of choice is used. I don't really know what to call the area that it comes from. It's a very interesting result in any case. I'm going to call it set theoretic geometry. Let's put a question mark there, because I'm not really sure what area to assign it to. Nonetheless, it is definitely mathematics that follows that one has to accept if one accepts the axiom of choice. Okay, so we're going to then move on to now to finish this first part of the lecture, the statement and proof of Vitali's theorem. Because it's an axiom, it relies on the axiom of choice, we need to do something we did not do in the previous lecture, which is we are now going to assume, at least for today's lecture, the axiom of choice. So henceforth, for today's lecture, we're going to add the axiom of choice to our axioms. We assume AC. Let's put this in a box because this is obviously important that we're making this assumption. Okay, so we're now going to work with our original set theoretic axioms together with the full axiom of choice. But in fact, we're going to use the axiom of choice in an equivalent version, which is not one of the equivalents we gave last week. So I'm going to state the equivalent version. So in fact, we use AC in the following equivalent version. So let's put a bullet point. This is an equivalent statement to the axiom of choice. Every set of equivalence classes has a system of representatives. Or let's just say a set of representatives. I think people sometimes say system of representatives, but it sounds system's a bit of a big word to use in the circumstances. So a set of representatives. So in other words, let's write this explicitly. So if we have an equivalence relation, on a set X, then there exists a subset K of X with the following property. For every element little x of the set capital of X, there exists a unique element Z in K such that X is related to Z. So what this is saying is we've got an equivalence relation on the set X. So that partitions the set X into a collection of equivalence classes. So we would write the quotient set X divided by the equivalence relation that's the notation for the set of equivalence classes. And K is choosing from each equivalence class one element. So K is a set that contains exactly one element from each equivalence class. So we think we call those elements each such element is a representative element for its equivalence class. Now it is rather straightforward along the lines of the sorts of exercises you did in the exercise class this week. It's rather straightforward to show that this is equivalent to the axiom of choice. So again, I'm going to say exercise. Let's maybe call this star. Prove that star is equivalent to the axiom of choice. Okay, so let's move to Vitali's theorem. So Vitali's theorem addresses the question can we measure the length, let's put that in quotes, because we're kind of trying to give a definition of length in the process, of an arbitrary subset of the reals. So such a measure of length would be given by a function, lambda, that assigns to an arbitrary subset of the reals. So that's so a subset of the reals, the set of all subsets of the reals is the power set of the reals, of course. So that it'll assign, given a subset, it will assign it a length. The length will always be a non-negative real, or possibly infinity, because of course the length of the whole subset of the whole real line itself is infinite. It's an intuitive notion of length. So for example, so consider the subset that we take. I don't know, there are many versions one could give, but I'm going to take 0 to a quarter and union that with a half to 5/8. I'm going to union that with 3/4 to 13/16. And then I'm going to union that with 7/8 to so whatever it is, something over 64. So 7. Sorry, I want over 32 here. I should have written notes for this beforehand. It looked like something that would be easy to calculate in one's head as one went along, but it's always, one can always get, it's 29 over 32 and so on. And notice that this subset, hopefully you can see the pattern now. Here we've got length 1/4. Here we've got length 1/8. Here we've got length a 16th. We've got length a 32nd. And we're continuing the series here. And so the set is this countable union of intervals, and it would seem perfectly natural to assign this should really, there's almost nothing else it could be. So we should have, so this should have length the sum of all these numbers, which is a half. So it doesn't seem difficult to assign a length to a notion of length to this subset. So notice this subset has a gap from 1/4 to a half. We don't count that gap in its length. We're not talking about the length from the smallest element of the subset to the largest element. There's no largest element in this case, but the elements of the subset converges to 1. So we're not talking about the length from the smallest element to the largest element. We're talking about the length of all the real numbers that have been included in the subset. So the real numbers between a 1/4 and a half were not included in the subset, so that part does not count towards the length. So the length of the real line actually occupied by this subset is naturally the length of a half. And Vitali's theorem is going to say there is unfortunately no such sensible way of assigning there is no sensible way of assigning lengths to arbitrary subsets. So what did I write? So Vitali's theorem. So we're going to say, so it is, there is no function lambda from power set of the reals to the non-negative reals together with infinity that satisfies three conditions. And these are three conditions that we would expect our length, we would want any length function to satisfy. So the first condition is that the length of an open interval from a to b, where a is less than or equal to b, is just, so we're including all the real numbers strictly between a and b, the length of that, of course, should be b minus a. So where a is less than or equal to b. The second condition is going to be what justifies our sum above, so that we calculated this length being a half. The second condition is going to be that if we have a set of subsets of the reals, I, which is countable, so it is a countable set of pairwise disjoint subsets of R, subsets of the reals. So just like here, the set of all these intervals here is a set of pairwise disjoint. So this is a countable set of subsets of the reals. We are unioning them all together, but the set containing all these intervals is a countable set of pairwise disjoint because none of them overlap. No two of them overlap. So a countable set of pairwise disjoint subsets of the reals. That's an example. And here we're unioning them together, and we say when we union them together, the length of the union is the sum of the lengths of the individual parts. So we're going to exactly ask for that. So then the length of the union over all the subsets X in the family curly I oh well, we can even write that in a simpler way. It's the same thing. Length of the union is the sum over all the sets. It's a countable sum, but that's okay. We can perform countable sums of non-negative reals together with infinity. That's a well-defined operation. So it's the sum of the lengths of the individual sets in I. So that's the second condition. And the third condition is, so this second condition, by the way, is called countable additivity. And the third condition is that if we have any subset of the reals, so for any subset of the reals, and if we shift the set by some displacement, by some fixed displacement value, that is, if we translate the set in the geometric sense, then the length of the set should remain unchanged. So if we shift a set around by translating it either up or down the real line, it should not change the length. So for any x and for any displacement, which is a real number, a displacement's a real number, we have that the length of the displaced set, which we'll write as x plus d, is the same as the length of x. So this is called translation invariance. And just to clarify, so here x plus d is defined to be so x plus d, that's just the set of all elements of the form x plus d, where x, so all real numbers formed from an element of x by adding d to it. Okay, so these are, hopefully you can accept, these are intuitive conditions we would want the length function to satisfy, and unfortunately we cannot satisfy them all. That's what Vitali's theorem says. And as I've already, the whole point that it's in this lecture is that it relies on the axiom of choice. Okay, so we're going to prove Vitali's theorem, but before proving Vitali's theorem, I want to note some consequences of the properties we've assumed for such a length function. So we've assumed 3 properties for a length function, but some other properties follow from that. So before giving the proof, we observe that any lambda satisfying the 3 properties above also satisfies some other conditions we would expect a length function to hold, but we did not need to add them to the assumed properties because they follow from the previous ones. So you can prove from it, it follows for 2 different reasons, in fact. The length of the empty set is 0, as it should be. The length of a singleton set is also 0. The length of the closed interval AB, we've specified that the length of an open interval should be b minus a. The length of the closed interval is also b minus a. The length of the whole real line itself is infinity, as we would expect. I want to make sure my infinity looks more like an infinity by not having a gap between the 2 halves of it. And lastly, that if x is a subset of y, then the length of x is less than equal to the length of y. And so once again, these consequences are all rather straightforward consequences of the properties I assumed in the statement of the theorem. So as I often do, I'm going to leave the verification of them to you. It should not take long. So exercise, verify that these are indeed consequences. Okay. So with this at hand, let's proceed to the proof of Vitali's theorem. And the core idea of the proof is to partition the real line into countably many disjoint subsets, where each of the disjoint subsets is a translation of every other of the disjoint subsets. So we partition the real line. So essentially, if we take one of the subsets, then we can recover the real line by countably many translations of the one subset we've taken. And that gives us the real line as a disjoint union of countably many sets, each a translation of the other. So how can we do that? Well, we do that by, we define an equivalence relation on the reals by x is equivalent to y if and only if their difference is rational. So y minus x is a rational number. So this is an equivalence relation on the reals. It is therefore also, it restricts to an equivalence relation on any subset of the reals. So this restricts to an equivalence relation on 0, 1, or the open interval 0, 1. So by our reformulation of the axiom of choice that we had on the previous page earlier today, we can let K be a set of representatives for the equivalence relation for the equivalence classes over 0, 1. So let K be a set of representatives let me emphasize that K is a subset of the open interval 0, 1 of representatives of equivalence classes. So I'll just say for the equivalence relation, or let's say for equivalence classes on 0, 1. So if we scroll back, it's explained what that means here. So K is a subset of 0, 1 such that for any element of the interval 0, 1, there's a unique element of K that is equivalent to it, so that is the difference between Z and K is rational. But because every element of the real line can be shifted by a rational to end up in the interval 0, 1, then it's easy to see that it holds that for every real number x, whether or not it's in the interval 0, 1. So let's just neaten that. For every real number x, whether or not it's in the interval 0, 1, there exists a unique representative in our set K such that Z is equivalent to X. Okay. So because K is a subset of 0, 1, of the interval 0, 1, so since K is a subset of 0, 1, we have, by the monotonicity property of a length measuring function here, we have that 0 is less than equal, so we're assuming, so let's actually, just to make it clear, sorry, I will come back to that, but just to make it clear that, so now assume we have, so we're going to assume for contradiction, assume we have lambda satisfying the properties. The properties in the theorem. So now the thing that I was writing before, so because the set K is a subset of the interval 0, 1, we of course have that its length is greater than equal to 0, because lengths are always greater than equal to 0, and the length is less than equal to 1, because that's the length of the interval 0, 1. So the question is, what number is the length of K? And we're going to first show that it can't be 0, and then we're going to show that it also can't be any positive number. And that way we're going to reach a contradiction. So let's suppose that the length of K is 0. Well, in that case, let's consider the length of the whole real line. Well, we know that's infinity, but the length of the whole real line is the length of, well, we can rewrite the real line as the union over all rationals of the set K shifted by Q. We can do that because of this observation here. So let's call this star. That every real number, for every real number there's a unique Z in K such that Z is a rational shift of that real number. So this is by star. But because there's a unique rational number, that means this is actually a disjoint union. And so this is the length of the disjoint union is the sum of the lengths of the individual parts. So each individual part is K plus Q, is the shift of K. So this is by countable additivity. And we're using also part of star in the process to get that this is a disjoint union. So let's maybe, because I've put star up here, let's emphasize that here this is a disjoint union. Okay, so it's the sum for every rational, so we're summing infinitely many summands, and each one is the length of k shifted by the relevant q. But by translation invariance, the length of k shifted by q is always the same as the length of k. So here we're simply summing countably many times the length of k, and this is summing countably many times 0, because our assumption was that the length of k was 0. Let me just neaten that countable up there. And this is 0, of course. And this contradicts so we've concluded, using the assumption that the length of k was 0, we've concluded that the length of the real line is 0, but this contradicts the consequence we already have from our properties of the length measuring function. So this contradicts that the length of the real line is infinity. So we've reached a contradiction. Okay, so our assumption that the length of k is 0 must have been wrong. So it must be the case we must have that the length of k is positive. Let's just make that k neater. It's not neat. Let's do it again. So we must have that the length of k is positive. But now let's consider the length of the set where we again take a countable union of shifts of k, but this time we're going to countably union by over just rationals contained in the interval 0, 1. So for each of these we're going to take the countable union of, again, the shift of k by that amount. So once again, this is a disjoint union, and so this is going to be, it's obviously a disjoint union because it's a subunion of the previous disjoint union. We're just unioning fewer elements of, fewer copies of k together, fewer shifts of k. So this is the sum, again, of countably many things, countably infinitely many things for all rationals in the interval 0, 1 of the length of k plus q. So this is countable by countable additivity. And this is then, again, the length of the shift is the same as the length of the unshifted k. So again, this is the sum over countably many things indexed by rationals in the closed interval 0, 1 of lambda of k. So this is by translation invariance. Just wonder if I wrote translation invariance above when we used it. No, I didn't. So let's put that in. just draw an arrow to that equality, and this is by translation. Invariance. Okay. So we're summing lambda k infinitely many times, but because lambda k is a real number, it's certainly real because it's below 1. It's not infinity, but it's greater than 0. We're summing infinitely many, that number infinitely many times. This is infinity because, so this is infinity because lambda k is greater than 0. But when we look at this set, this union, we're unioning, so each set that we're unioning together is a shift of k. Sorry, I just need to, I've got a big wasp in my room, so I'm going to try and get it out. Right, we'll see what happens. I've opened my window. Okay, so we were at this union. So this union is, each set that we union together here is k shifted by a rational number that's between 0 and 1, and k itself is a subset of the open interval 0, 1. So what we note is that, however, the union over these rationals that are contained in 0, 1 of k plus q, this is a subset of the open interval 0, 2. So it has length, so lambda length, less than equal to 2. So this set can have length, lambda of this set can be at most 2, and here we've calculated that it is infinity. So that is, again, a contradiction. So we have a contradiction from the assumption that we had a lambda satisfying the properties in the theorem. Whatever lambda applies to k, whether it's 0 or whether it's a positive number, we get a contradiction, so therefore there can exist no such lambda, and we have proved the theorem. Okay, so that is the proof of the proof of Vitali's theorem. So, as I said earlier, the consequences that we're looking at are a bit discomforting or disquieting. They make one feel a little bit uneasy. So why should one feel a little bit uneasy? So in this case, what it says is there is no good way, the theorem is saying there is no good way of assigning a notion of length to a subset of the real numbers, to an arbitrary subset of the real numbers. So let's write that down. So Vitali's theorem says there is no good way of assigning a notion of length to arbitrary subsets of the reals. So how do mathematics cope with it? How do mathematicians cope with this? So mathematicians need to cope with this because it's a fact of life. So three possibilities are: so the first one is that one might weaken these assumptions on the assumptions in the theorem on the properties that the length function needs to satisfy. And one that people sometimes choose to weaken is this countable additivity. And one can weaken that to finite additivity. So it actually turns out to be the case that if countable additivity is weakened, is relaxed, so we have a less stringent requirement on the function, so it's weakened to finite additivity, where that means the obvious thing. Then length functions can be proved to exist. The proof is actually very difficult. However, there are two problems to this. This is not a good solution. So the first problem is finite additivity is not enough to do many things one wants to do with length. So finite additivity is not strong enough for applications, particularly towards using length in analysis, for example. So for applications one would like. And for example, with finite additivity, we would not be able to conclude our example. We would not be able to calculate that this has length 1/2. It need not if we only have finite additivity. And the other, even more severe problem is at higher dimensions, even finite additivity is not achievable for an. So at higher dimensions we're looking at, rather than length functions, we're looking at area functions and volume functions. So even finite additivity is not achievable. And I think this certainly happens at dimension 3. I think it even happens at dimension 2. Is not achievable. Don't quite know how to spell achievable, actually. Maybe this E should be there, maybe not. I shall correct the spelling before I publish the notes. Okay, so that would be one solution, but that's not a good one. So the solution that mathematicians tend to adopt is this. We can relax the, or let's say we can weaken the length function to a function that, instead of acting on the whole power set of the reals, acts on some set of chosen measurable subsets of the reals. So on chosen measurable subsets, those do get assigned, chosen measurable subsets do get assigned a length, either a non-negative real or infinity, where sigma is a set of subsets of the reals is a set of chosen measurable sets. So this, if one does that, one can keep all the three requirements on the length function. So all the three conditions in the theorem stay intact. And this turns out to be a very powerful framework for doing things. So this, as those of you, particularly those of you who've done courses on measure theory or probability theory will know, so this is the writing's getting messy. So this is the solution adopted by mathematicians. So this is how people practically deal with length in mathematics. But just to mention it, a third option is to drop the axiom of choice. So that would be another possibility. So when I've said adopted by mathematicians, let's just change that to preferred by mathematicians. And we'll drop the axiom of choice. That's the third option. But mathematicians don't want to drop the axiom of choice because if they drop the axiom of choice, they lose all the theorems we had at the start of the lecture. There we go. There are the theorems at the start of the lecture. But just to say, oops. So the existence of a length function of the form we were looking at from the whole of the power set of the reals to 0 infinity is consistent. So it is actually a consistent thing to have in the absence of AC. So the only problem is the axiom of choice. Okay, so that's the end of the examinable material. I do just want to complete this half by stating the Banach-Tarski theorem, which is going to be the subject of the second part, which is the optional part, which is going to be the proof of the Banach-Tarski theorem. But I want to put the statement of the Banach-Tarski theorem in this first part because I just want to show you all the result, because it is such a surprising result. This is the kind of result that gets discussed in popular science about mathematics. It's such a surprising result. I'll say something else about its surprise in a moment. I'm just right. So we're going to end with the statement here. So the Banach-Tarski theorem. Well, Tarski should have a capital T. So as I've told you, this is kind of a theorem in set theoretic geometry, and it's a very specific geometric situation. It's about the closed unit ball in three-dimensional space. So let B, so it's a set of real numbers, be the closed unit ball. So in other words, those of you who want reminding about what such words mean or how one defines things in geometry, it's the set of all points x, y, and z in 3 space such that their distance from the origin, so x squared plus y plus z squared, x squared plus y squared plus z squared is of course the square of their distance from the origin. But if we ask that the square of the distance from their origin to be less than or equal to 1, that's the same thing as the distance from the origin being less than or equal to 1. Okay, so we know what the closed unit ball of radius 1 is. So the unit means of radius 1. So the amazing thing that the Banach-Tarski theorem says is that then B can be partitioned as, so a partition means we express B as a union of disjoint subsets. And we're going to express it as a union of finitely many disjoint subsets. But we're going to split them into 2 groups, A's and B's. So let's put this is a disjoint union. Let's keep it black. So I'm putting this in brackets that it's a disjoint union because the word partitioned already says that it's a disjoint union. Such that there exists, and now I'm going to use some terminology that you probably won't know what it means, but I shall explain. So such that there exist proper, what are called proper rigid transformations. And this is, such things are combinations of rotations and translations. So hopefully you know what a rotation of 3-dimensional space is and what a translation of 3-dimensional space, that's an additive shift. So these are combinations of rotations and translations. And we're going to call these proper rigid transformations. There is one transformation for each of the pieces in this partition. So we're going to call them thetas, theta 1 up to theta m, and phi 1 up to phi n. So the thetas are for the A pieces and the phis are for the B pieces, for which it turns out the case that with these transformations we can recover the unit ball by taking the A pieces and applying the rigid transformations to them. So if we take the piece A1 and apply the rigid transformation theta 1 to it, and we take the piece A2 and apply the rigid transformation theta 2 to it, and so on up to the piece AM and the rigid transformation theta m to it. We do that, we get back the unit ball. And the point is, this is again a disjoint union. It wouldn't need to be. One can find rigid transformations such that if we apply them to these disjoint pieces, A1 through to AM, they were disjoint pieces. We can certainly rigidly transform them so that they're not disjoint, but we rigidly transform them in such a way that they remain disjoint. And then we've got, in the end, a disjoint union. We take that disjoint union and we recover the whole of B, and we get the same thing if we apply the phis to the B pieces. And that is the end of the statement of the theorem. Let me see if I can shrink it a little bit so we can get it all on one screen. There we go. So it is a really shocking theorem. You may not see that yet, but let me explain it as follows. We've partitioned the unit ball into m plus n pieces, disjoint pieces. So we've essentially cut the unit ball into m plus n disjoint pieces. We then take the a pieces. To each of them we apply a rigid transformation, which is just a rotation together with a translation. So all we're doing is rotating and translating the piece. We do this to the m pieces. We manage to do that so that we can put these m pieces together, the a pieces together, so that they together give us back the whole of the unit ball. And we can also do the same thing with the b pieces, and we can put those together so that those give us back the whole of the unit ball. So basically, by cutting up one unit ball into a finite number of pieces, and by rotating and translating those pieces, we've been able to reassemble them into two copies of the unit ball. That is really quite shocking. It's something that would be very useful to do if you could have balls of gold or something like that, and one could really practically cut a ball of gold up into a finite number of pieces and reassemble them to get two balls of gold exactly the same size as the original ball of gold. Now, of course, that's something that in practice is not going to be possible, so it's very weird that in set theory one can do this. And one can do it, of course, because, well, we're going to use the axiom of choice, and we're going to use the axiom of choice to define pieces a1 through to am and b1 through to bn that are very peculiar. They're kind of, I like to think of them as sort of aerosol pieces. So an aerosol is like what you get from a spray can. It's like very fine droplets in the air, and essentially the pieces that we've got, they're not solid pieces at all, but they're just collections of points given by the axiom of choice, and they don't have shape or size, so to speak, and because of that you can sort of put them together in funny ways. So how this works mathematically is going to take quite a lot of work. It's a very interesting proof, and as I say, it's a very shocking result. It's such a shocking result that it's often known as the Banach-Tarski paradox. So if you look up online Banach-Tarski, you're going to find more hits for Banach-Tarski paradox than you are for Banach-Tarski theorem, because it's such an unintuitive result. Nevertheless, if one accepts the axiom of choice, one is forced to accept this result as a mathematical fact. Okay, so that's enough for this part. As I said at the start, the Vitali's theorem and its proof, that is examinable material. The Banach-Tarski theorem, it's good for you to understand the statement of the theorem. The second part of the lecture is going to be a proof of the Banach-Tarski theorem. As I've already told you, that is optional. It's purely for those of you who are interested in seeing such a proof. Okay, so I shall be back shortly, or at least eventually, with that proof. For the rest of you, I'd like to just say that there is no lecture next week because the lectures are timetabled on Fridays, and next Friday is a holiday, the 1st of May. So the next lecture is going to be 2 weeks from now on Friday, the 8th of May. Okay, so that's enough for this half. Bye for now. And for those of you interested in the proof of the Banach-Tarski theorem, see you in due course.